One of the things I'd like to describe to you today is my experience in understanding and developing a strategy towards international development, and how do you approach that from a design space, from a financing space, and from a research space. And while I talk through those topics, what I'd like to do is actually take the first half to describe how my thinking has evolved and my life choices and career choices have evolved over the last 20 years, and then lead into some more specific examples thereafter. Because particularly where you are now in your education and you're looking for careers, you're probably in that mindset of what type of occupation do I want to have, what type of career do I want to have, and what type of life challenges or global challenges do you want to solve. And so hearing from folks and thinking about the types of experiences they had, the types of questions they asked, might also help inform some of your own thinking in that regard. So my work actually in development, or I would say service, started when I was in my early teens, and I grew up in rural Iowa, a town of 5,000 people, northwest Iowa. So as you would understand in the Midwest, also being in the Michigan area, you're well aware of what a tornado is. And so I actually started doing disaster cleanup, disaster response for the Salvation Army and other units. Sometimes it was providing food, other times it was rebuilding homes. Sometimes it was mundane, as being a group of 100 people walking through fields, picking up pieces of metal and trash, because you can't run farming machinery through the fields to potentially damage assets that are anywhere between $500,000 to $1 million per asset. So this is how I got started doing development, in addition to doing Meals on Wheels and some other volunteering activities when I was younger. But when I got to college, I knew I wanted to be an engineer. I wanted to work in energy, and so I started to say, hey, I was, getting big into biofuels. Maybe I should go into biofuels. So I started to work in biodiesel, did research for 3 different summers on biodiesel formulations, mixtures of soybean oil, animal fat, et cetera else. How do you mix it, what temperatures to get the highest yield and the lowest amount of soaps and et cetera in the actual fuel that would cause degradation in your machines. So I was enjoying this, but after several months of doing this work, it just wasn't meeting my own personal need. And one of my personal needs that I would find is that in the laboratory, the thing that was missing completely was other people. So I decided that I needed to make a career change, because for me, as an engineer, it was too impersonal to be working in a laboratory 24/7. And so then I changed my career and still focused on the energy sector, changed that work to international development, focusing on cooking stoves, solar hot water heaters, lighting solutions, et cetera, around the world. As that started, it was is and has been and is expected to continue to be a large challenge for energy poverty. So 2.7 billion people using solid fuel cook stoves around the world, leading to about 5 million deaths per year that we measure that relate to indoor air pollution. 1 billion people without water, and 1.4 billion people without electricity. And even there's going to be tens of billions of dollars invested into the sector over the next 20 years, the incidence of these numbers, or the incidence of poverty, is expected to remain largely unchanged, principally due to sub-Saharan Africa. So in the South Asia and East Asia, China, India, Vietnam, Cambodia, Indochina are actually developing quite well to a larger market-based economy, but most of sub-Saharan Africa is being left behind, as many would say. So as I was looking at this type of work, I was also reflecting at the time of the Engineering Code of Ethics and also the Hippocratic Oath, and I was seeing a lot of really good-intentioned, well-intentioned volunteers that you would classify maybe as hobbyists, doing work that was very heartfelt, but didn't have a firm engineering design process to understand user needs, to firmly go through the mechanical, electrical, civil, and other design processes, implement the solutions, and then actually measure and evaluate what happened after. And there was also no standards, no codes. So as volunteers, we don't necessarily IEEE, ANSI standards, ISO standards, UL, IEC standards, they don't always apply to our international volunteer-based work. So there was a lot of work being done that wasn't very well regulated, and as a consequence, you had technologies that might actually be doing more harm than good. And so that's where I started to take into account that medical practitioners' insight of the Hippocratic Oath: first, do no harm. And it's not only physical harm, but it's also economic harm, cultural harm, and social harm that could be caused by your design strategies. So in this particular work, this is for my master's, I designed a series of testing protocols 10 design principles, and a $100 test kit, which replaces about $50,000 in equipment in a specialized laboratory. And we implemented in over 20 countries. It's been translated, and it's been used on over 150 stoves. This is the safety work. There's also work in durability, emissions, and performance, which has now been adopted as an ISO international standard, and you can go download it, and then there's regional testing regimes for cook stove safety around the world. This work I started almost 12 years ago. It's taken that long to actually have a formal ISO standard. So if you hear anyone talk about standards and protocols out there that are regulated or by ANSI, ASME, wherever they are, that's a multi-year process. So it's a large investment to do and work in developing standards. At the same time doing this work, I started to travel around the world to different countries, Honduras, Belize, Mali in West Africa, South Africa, 7 months in Vietnam, 3 months in China, some time in Indonesia, Philippines, India, and a few other countries. And I was seeing lots of projects that had simply failed. And so that was another big issue that I saw. A statistic to throw at you is that 9 out of 10 cooking stove projects in the 80s and 90s failed within 1 year. And so that was, again, really well-intentioned people, not a very good technical design strategy, user engagement, community engagement, and then also what's the business mechanism to financially sustain the technical solution after you depart. And so I saw this work going in, and there was countless failures that you could see. Sometimes it was as simple as saying, hey, we picked up these water faucets at the Royal. We picked up these water faucets at Home Depot because they were available, low cost, going to bring them to wherever they are. And they're good for about 10,000 turns, 10,000 uses, which is fine for the outside of anyone's home because you're going to be watering your lawn maybe once a day, a couple times a week. And so these faucets can last about 20 years. Now think you have a village with 100 houses in it, and each person goes to this water, let's say 1,000 actually. Let's do the numbers a little easier. 1,000, and each person is going to go to these types of faucets, once a day. Then you take 10,000 divided by 1,000, and you get 10 days. Or if it's a a smaller case, 100 families, then all of a sudden it's just good for 100 days. 10,000 divided by 100. So the amount of longevity of the technical solution is actually very minimal because you didn't understand user behaviors and design problem. Up at the upper right is actually another context that you wouldn't find in a laboratory. This is a solar hot water heater that I observed as I was on a tour of southern Mali. It's a broken solar thermal collector on the bottom. And as you start to ask questions about what was wrong and how they get broke, it was goats. So goats like to jump on things, they like to get high, so they jumped on top of the solar hot water heater in less than a day, as I was told. So how many people consider goats in the engineering design process? Where does that fall within your QFD or your Gantt charts? Probably nowhere. So doing the field assessments, understanding and working with people is undoubtedly important in that regard. So how might we garner and gather some more of this data? So we started to look at this largely down here is, we're focused on the experiments in the laboratory. Surveys and bubble sheets get us some information, but it really doesn't, no one's described by a bubble sheet. So how can you do focus groups and participatory observation to round out your design insights? And so what we came to is four forms of information. So you can walk through a community or in this room, and you can see that someone has made an action, the color of their notebook. And so they've picked a notebook up and they've chosen that notebook. They chose it out of a series of different colors. And so that's what you can observe just without asking questions. Now you need to know a little bit about the choices that are out there, but you need to be able to immerse and ask questions and do participatory observation to get to these two down here. And those are very, very critical. Because just off of that information, I can't go design a lighting technology or a cooking stove. So then, why might you have chosen, the color blue over the color red? Was it due to your university affiliation? Do you like blue? Is there some bad connotation for you with red? What might it be? And then at the end, that allows us to then formulate a viewpoint on how that judgment guides other decisions in life. And so by living with families, by engaging, asking questions, doing deep interviews, participating in the entire day, collecting wood, rearing children, I spent months with different types of families. I was able to garner and collect viewpoints that led to design decisions which have no prior relevance within the community, or no prior relation, I should say. So electricity hasn't been in the community before. So how do you conceptualize, or what does a village look like, or a home look like now that it has electricity? So let's do an example. So when I was in college, I had this vehicle. Does anyone know what this vehicle is? A Volkswagen? I realize now where I'm talking, I probably should have had a different vehicle up there. So this is a Jetta TDI from Volkswagen, and so I made an action. Tell me out there from the user audience, what choices did I have? Other types of cars. SUVs, yep, different brands. So I went to the lot and I got this vehicle. So then you can consider, okay, Nate picked this vehicle out of a lot of other types of cars. Now comes the question, why did I do that? So that's the judgment. Ask me some questions which you might think would lead to why I did that.
Notice your budget.
Yeah, good. Financial question, very good.
Typical driving distance.
Typical driving distance, perfect. Yep.
Things you'd be, like where you'd be going to and from for work versus play kind of thing?
Yep, personal and work uses, very good.
How'd you feel about diesel versus gas?
That's another really good question. So now all of those, it was part financial, it was largely the use cases and the distance, and then it was also diesel because it was better fuel economy. So now the judgment is, why did I make that? So why did I choose X over Y? And so Z is that Y, the Y behind that. So it was 1 out of distance, it was 2 out of fuel because I could get 40 plus miles per gallon in fuel economy. And remember, back to my earlier life as working in biofuels and etc. else, I was worried about energy use in the planet and things like that. And additionally, I had a car that broke down a lot, and I wanted a reliable vehicle. And so not only was it a bit newer, but the diesel engine ran, for me at least, I sold it and it was like 225,000 miles and I got rid of it a couple years ago. So that was really important to me, that I had something that would last a long time and then I didn't actually, waste more materials in that way. So from those types of whys behind it, what type of viewpoint that you could describe to me? What's important to me?
Earth reliability and value.
Okay.
Financials.
Good. Financials. Reduction in waste. Good. Good. Anything else?
Durability.
Durability. Excellent. Anything else? So, reduction in waste. Other types of things I use. Refillable water bottle. A lot of things in my life actually are intended to reduce items that go into the landfill. And so by observing, asking questions on this particular product stream and those behaviors, it actually applies to a lot of other categories of life. So that was extremely astute. Another one from a more personal note, this is my wife, Jen. So we have made a couple of particular actions in these 2 photos that I chose. Describe them to me. What do you see? Fun, good. And essential quality of a marriage, by the way. Any other things you see?
Active lifestyle.
Active lifestyle, good.
Water. Breathing.
Hydration, good point.
Cooperation.
Cooperation, yeah, absolutely. Particularly when you're riding a tandem, it would be hard not to cooperate on that particular device. Anything else? Yep.
You like traveling?
Yes, we do like traveling. So let me pull a couple of those together for you. There's biking and there's traveling. Both of these come for travel. We do like to have a good time. And so we are intending in the next couple of years to do a little bit more international travel. And we've actually just picked up a tandem to go bike around the world. So we have bike tours lined up in the Highlands in Scotland, in Australia, and then a few other parts of the world. Because we want to see a little bit more before kids come along. Biking and exercise is really important to us. It's how we met, and it puts us as a team, which is what a marriage should be. And we have a lot of fun doing it, which is you see there. So, good, excellent. So think about those types of considerations when you're doing your design work. And so this is an example I'm going to walk you through in Mali. The particular village is Nana Kenyeba. It's the largest of a series of 8 villages, which total population out of those are 10,000 people. And they're about 3 hours southwest drive using a 4x4 outside of Bamako, which is the capital. So Fatimatu Keita on the left, and I spent a significant amount of time together with her and her family, helping rear the children, gathering the fuel, the food, as well as at the same time not only understanding the user and the use cases and the local culture, but then also taking measurements in terms of emissions, fuel use practices, etc., to kind of get a complete perspective. And the way that we describe this in one contextualized way is called an engineering ethnography. So you're getting your engineering information. You're not necessarily spending years doing an ethnographic anthropology study, but you're spending weeks with someone to understand very deep-seated needs and design requirements. And those are undoubtedly not just about the technical system. It's about how does a person's use cases and behaviors change throughout the year as seasons change, as it's rainy or it's hotter outside. So for example, one of the insights was that you actually need an indoor kitchen and an outdoor kitchen because during the rainy season you're inside, but during the hot season you're outside because it is too darn hot in the kitchen. I recorded temperatures in excess of 140 and 150 degrees Fahrenheit in the kitchen, absolutely no problem. And you can imagine being in there for hours and then thinking about stepping into a sauna and it says don't be in here for more than 15 minutes. For the human system, different people use stoves in different ways, as well as noting that the children being on the back or around the fire creates a potentially unsafe environment for kids to be around an open fire. So we took this information back and we said, okay, how do we remove pollution, save time, and provide value for the product? The center there was a very useful observation that no one had really went and followed a variety of families around for a day, women, men, children, everyone, and then actually categorized it using task flow analysis for where the heck do you spend your time during the day. And so what's intriguing from that is on an average for a typical female adult in Mali is that almost 2/3 of your time is spent on cooking or energy. So they'll be gathering wood, chopping the wood, bringing the wood back, drawing the wood out, preparing a meal, getting the food ready, gathering water which goes into the stews, and at the same time you have to take care of the kids and et cetera else, but the men sure the heck don't do anything. So you have a very, very busy day, which you should realize right there if you provide whatever it's going to be, a solar stove, which is going to take more time for things to cook, not going to work, particularly since breakfast is served at 5:30, lunch is served at 7:30 a.m. before people go to the field. The other thing is that from a use behavior is there's a fairly efficient cooking technologies or cook stoves, but you need to tend the fire every couple minutes. And if you need to go get water, maybe wait in line, chop up the vegetables, take care of 6 kids, do a variety of other activities while you're also cooking, you don't have time to play with a fire. So imagine what you would like in your own kitchens and stoves. You turn the burner on, it stays there, it's a consistent amount of heat. Why do we feel that imparting technologies that we wouldn't use onto other people is somehow appropriate or a good idea? And that's where we came with here, is that if you took in the laboratory the rated impact of what you think is going to actually be saved, so 50% fuel use, and then since people use it differently than you do in the laboratory, much like your fuel economy reduces in your car versus what's advertised, some people don't adopt it, and even if they do adopt it, they might not use it all the time. So think to your own, you might have a toaster, an oven, a microwave. Not one device is actually going to work for you. And think as well that the cooking stoves, they're called cooking stoves, but actually they should just be stoves, because there is hot water heating for bathing, washing, and there is also food processing applications that occur on these same devices. And so trying to encompass all that was impossible. And so my assessments that was done, the rated impact of 50% was actually closer to about nothing. So if you have a just brute force focus on thermodynamics, you're going to get nowhere. But if you have a user-centered design process which focuses on something that's versatile, used across a variety of different cooking needs, user-friendly, and then also as a product family, like we have in our own kitchens, you're going to have a far greater impact on the holistic side. So With that in mind, I kind of came to this conclusion, and several other people have had similar styles of quotes, is you don't design for what people need, you design for what people want. In engineering literature, you're going to hear a lot about user needs, and that's fine. But realize that it's easy to have a conceptualization that's biased on what someone needs. Whether it be Maslow's hierarchy or whatever that is, you need energy, water, food, shelter, without actually asking the questions of, do you even want this? So that's one of the reasons why 9 out of 10 cooking stove projects failed early on, is because they had people need clean or no smoke in their kitchen, without asking what might you want to make the experience better for you. And noting as well, I'm sure there's people out there that barbecue. The taste of food on a barbecue is different than if it's on electric griddle. Same type of thing if you're cooking over an open fire. And so if you remove some of those cultural, and food is extremely cultural. So if you remove some of those natural tendencies, those cultural tendencies, it actually divorces someone a little bit from what drives them as human beings. And so one of the solutions that we design helps our cook stove projects in Honduras, Mali, Vietnam, and other countries in the Pacific Rim, is we went for a fuel stove combination and the Urja in the upper right, that's principally in India, but it's in the hands of about 2 million households worldwide. And it uses locally sustainable fuel, and so that is compressed agricultural waste, peanut shells, cassava waste, corn stover, rice hulls, etc. So we designed it for modularity. It was interesting. The design made a lot of sense from a manufacturing standpoint, because imagine cups. This one isn't as sustainable as my other one. Actually, yeah, it is. It's green. So the cups, much like stacking them, so it's conical, so it stacks easy for shipment and mass manufacturing and shipping in the region. But consumers, almost all of them wanted something that was square. So this is, remember that action, choice, judgment, etc. So probing, focus groups, consumer mock-ups to understand before we did all, let's create 100,000 and find out they failed. Consumer mock-ups and focus groups is, it looked more durable. The actual measured durability was almost no change, but it looked more durable. And so there was actually a far larger price preference or consumer purchasing preference if it was in a more square shape. And so we ended up going with the square shape in the end design. You can buy these 5-kilogram bags, and it cuts your fuel costs down versus kerosene or coal by about half. So if we have this in different countries, it wasn't just as the engineer on the team. We had a marketing person, a supply chain person, a channel person. So supply chain getting it to the point of manufacturing, channel getting it to the user, other financing people. So it was a very holistic team in that way. And one of the questions that we asked is, where do you manufacture everything? Do you bring in raw parts? Do you assemble things in another country? Do you ship it over? And that was a very fantastic learning experience for me in terms of how do you deliver something to low-income families that provide a sustainable profit margin for maintaining repair parts, and then also growing your scale. And that is extremely important to consider. So there are certain projects which definitely warrant international aid or startup costs, and I have a lot of examples of that. Once you transition, you want to be able to transition away from that, because you want to make something locally financially sustainable, so that when you leave, because you're not going to be around for 10, 20, 30 years potentially in the community, of what is a local mechanism of sustainability, and finance is a big part of that. So learning that you can ship in raw materials with a 5% tariff, but if you ship in a fully manufactured assembled part, it's going to be a 30% tariff. And so then do you work with these companies in this country, or these companies in this country to do it? And I was working with BP on this one, British Petroleum. They did a really good job of a socially driven product line, and it's called Emerging Consumer Markets before it was bought out about 8 years ago. This will just walk through briefly. So, and this is an example from South Africa, taking and assessing locally the amount of available biomass that would then go into producing the amount of pellets that would be needed to meet supply requirements or demand requirements in each locality across the entire country. Noting as well that biomass is available at only certain periods of the year when you're doing harvesting, and so then your production is going to be high. And some of the fuels have a higher moisture content, so that means it's going to rot over time. So then actually through that experience, we needed to work with coatings, which actually restrict the flow of water or moisture, which are actually commonly used in dog food. And so then all of a sudden you're like, okay, well now you have this, and it's from dog food, we put it on the pellets, but is there any worries with the pollutants that would come if you actually burned these? So that was the next phase of questions. That was when I actually transitioned from BP to come back to the United States, and I'll get into that. This just briefly, going through and developing not only the technical needs, the supply requirements, everything to get to the user and still maintain that high cost margin. And through this work, looking at not only the domestic cooking sector, but then also electricity, which is almost a rounding error there at the bottom, very small in many villages and locations around the world, but everyone wants lighting. So remember, user needs versus user wants. Everyone wants lighting. Everyone wants more electricity. So there's phones, there's radios, there's televisions. Everyone wants that. They don't want a cooking stove. So there's a lot of good you can do with having electricity, water treatment, etc. Powering clinics, obstetrics, primary care facilities, a lot of good you can do. So I shifted focus actually in my career, still doing rural energy, but from thermal sciences to electrical engineering. And I shifted that about 6 years ago. And part of the reason why I did that is that was just as I was finishing my PhD. And I did 2 years for a software company out in Colorado doing microgrid design. So it's small, decentralized off-grid power systems for remote communities. And to get some more experience in software development, but then also electrical engineering before coming to Arizona State University about 4 years ago. And part of my reason and rationale for that is, one, I can still do a lot of international benefit, but I was looking at my career and what I wanted to do as well. I wanted to be back in the classroom. I wanted to work with a team of students and professionals to design technologies and do it in a way that we create learning and educational paradigms that focus on global good. And so I really wanted to get back and do that. I could not really do that well being a cooking stove expert because there really wasn't much financing. There really wasn't much research funding in cooking stoves. But there's a lot of funding in how to move electrons around and how to control them. And that's from the Department of Energy, USAID, Trade and Development Agency, a lot of NGOs, even the Department of Defense, a lot of different groups that were very willing to fund energy projects. And since the basic principles of how electrons move, they don't care where you're at in the world, they're going to move the same way. A lot of the insights that we could design domestically could translate internationally, and then vice versa, which has been a very beneficial strategy to take. So as you're thinking about the next step in your career, thinking about what you want to work on, how you want to work on it, but then how do you group the projects or problem sets together so you can be flexible as funding streams change or as projects change. And that came to the Laboratory for Energy and Power Solutions at ASU. So I have a 25-person research team. We're a little bit unique because we're about half industry funded. We're very applied funded. Typical metrics around research university in the United States is about 3 to 6%. And so we're very applied research focused. Yes, we do basic science. We have funding in that area of work, variety of stuff. But we are very, how do you take the design sciences to the applied research to prototyping to field testing and then commercialization? How do you get things out into the hands of users and scale? We do work a good amount in microgrids, and microgrids is just, actually the world started with microgrids, not these major electric grids that we have today in the United States. Whether it be sugarcane plantations in Hawaii and elsewhere that slowly amalgamated together to create the national, or statewide, I should say, electric grid. A lot of the off-grid mining operations, islands, communities started that way. So we do simulation work and we do physical hands-on testing in our 1-acre microgrid laboratory. And the goal of that is to take ideas to prototypes and then turn those into real implementable solutions. And a lot of the students in our lab work very closely with our industry partners because they want not only the research experience, the educational experience, but then that what is it like to work in a business or for an NGO when you do implementation projects. And that's better done outside of a university. So there's a lot of good you can get in a university, but what can you get from other mentors and projects? I'm going to skip over this. So I'm going to go into a series of different examples, not just cooking stoves, but a variety of different types of work. And I have a couple of videos to show you as well, because everyone likes videos, particularly on a Friday. But I wanted to stop and pause. Is there any questions that anyone has right now? Yes?
Yeah, so I'm actually really curious. In this kind of work, I spent like a month doing ethnographic interviews in Nicaragua a couple summers ago. And so even, when I think about living in a community that you're otherwise, not familiar with, even for a few weeks and following them around like every day, I still would have a challenge like really truly understanding them and their motivation and trying to reframe kind of how I look at their situation versus like how they view their situation. And I don't know, like what kind of tips do you have for being in that situation and really viewing it from their eyes rather than yours, being in such different kind of situations in general?
One thing that I found helpful for translating insights across cultures and experiences is colloquial metaphors. And so how, like we would use here, like you knocked it out of the park. That's a very American common adage. So what types of stories or metaphors can you garner and learn from the local cultures that help inform and then relate to what you're doing? And that's helpful. It's much like when the movie Aliens was pitched. This is a bit of a tangent. In Hollywood, they were doing a horrible job getting it sold, really, Ridley Scott and folks. And so they said, and you can see it in the book, Made to Stick, they called it Jaws on a Spaceship. And so it was like everything you needed to know in like 3 to 4 words. And those types of experiences that you can garner from storylines or adages or metaphors from the local culture translate a massive amount of information. And then working with what I would classify and looking at social science literature as a gatekeeper who not only provides you the introduction to the community, but then also the translation for how your observations and how their experiences pertain to your own mental framework. And those people are not always easy to find that have an experience in the local culture, but then also yours. I've had the privilege of working with some very good people. I've also had the privilege of having $10,000 in hand, dropped off in a country, and come back in a month with some insights. And so that was intriguing. So in terms of other practices, there's a few things that I can provide in terms of framework for where you put your information that might also help think through that for you. Yep, and I'd be happy to follow up on email or phone call to chat more about your work. Yep.
So there's a lot of work around microgrids that's occurring specifically in Western Africa. But oftentimes as engineers, we don't think about the political and economic factors that might influence adaptation. So for example, Ghana, the majority of power from Ghana comes from the Volta River, hydroelectric dams and things of that nature. And they have agreements. So there was a development company that came in and built 3 high-rise towers. You can see them when you land in Accra. And those towers, as a part of their development agreement, they have to have power 100% of the time, even though the rest of the country suffers brownouts. And as a result of that, that changes the intelligent distribution of energy flow during certain times of the day. I mean, as an engineer who's trained to really think and from an engineering perspective, how important is it to really understand the political, economic, and social arena, given that, they're going to have to sign off on any type of development that you do within the country?
It's super important and even more challenging in the power sector because you're connecting to the national electric grid, which is a heavily regulated entity regardless of where you go in the world. Rolling blackouts are common in a variety of different countries. One thing, just as a side note, in the United States, each utility has a rolling blackout schedule that changes periodically throughout the year. So if there is a blackout and they need to shut a period of the city down, it doesn't disadvantage one population or another. And so that's actually law, that's not allowed in the United States. While at least you maintain critical operations such as hospitals, et cetera. So in Ghana, one of the considerations that I found interesting in Ghana, Nigeria, Kenya, Tanzania, and I have some examples in Tanzania later, in addition to this one on Mali, is that the local energy policy is extremely different. So sometimes it's a national utility, other times it isn't. Sometimes it's a national-owned utility, and anything that's built anywhere is owned by them. And so even if you don't connect to the grid, or if you do connect to the grid, they claim ownership on it. If you do connect to the grid, you, in other countries, I think it was in Nigeria, you can connect to the grid and own it so long as it's not over a certain kilowatt rating. So let's say 50 kilowatts, which would be about 20 homes in the United States. So those are extremely important to understand, and that greatly influences what you can or can't do. Another thing that I've seen in that regard is that I've walked through some communities that refused to work with the national utility, and so they had the national utility distribution infrastructure installed to all the homes. And then when the national electric grid went down for 3 to 6 hours a day, there was a local grid that took up the power output, so backup power, very reasonable strategy. The unfortunate part, because those two players couldn't work together in that constrained policy environment, is that they actually had to install another distribution system. So now you're doubling the cost of copper that you're putting into a community, and you're talking hundreds of thousands of dollars, but copper is extremely expensive right now. And those policy agreements were very challenging to get around. One thing that we've done I don't much talk about it here, we have a vocational education program. It's been a 5-year USAID program where we've trained about 1,200 people worldwide. And it trains technicians for solar PV installation and maintenance. It trains individuals, such as folks in this room, that would potentially be the trainers that train hundreds of people at the end. And then it also trains, getting to your point, policymakers. And so we actually go in first to work with the policymakers before we do the technician education. And it is not uncommon where the policymakers do need some insights, even if it's like, here's what the other countries are doing, a reference guide. We might be able to do a better strategy, particularly when you think about policymakers, what happens in, how do you support economic development? So how does your policy change or reform facilitate private influx of capital that could then benefit your people? Rolling blackouts are a big problem. ESCOM, the national utility in South Africa, experienced this quite horribly. I think it was about 5 to 10 years ago, that time period, and I was there about 10 years ago. And you'd be in, a Sheraton or a Hilton, didn't matter wherever the heck you were, but the power would go out, and the power would be out for 5 to 6 hours. They had rolling blackouts 2 to 3 times a week, and then my trips into the communities was even worse than that. And they've gotten a bit better, but some people have made unfortunate decisions about how they do their integrated resource planning, which is what do you install for power assets looking out 5, 10, and 20 years into the future. They've poorly planned for load growth for more people, but then also installing equipment that does well in the short term, but not in the long term. So like if you have a reservoir and you install more hydroelectric turbines to provide power in the short term, do you expect as much rain in the future? Are you going to be drawing down your reservoir? And so there's repeated examples of that. The last point that I'll mention to you, because this is a really good lunch conversation, because I feel like I'm going to take a long time talking about it, is that I'm a renewable energy advocate, but I realize how challenging that is for the utilities. And I work with and advise several utilities, and I work for public utilities commissions that regulate these utilities. You take a regulated monopoly and then you throw in a lot of unregulated businesses that disrupt that traditional technical and business mechanism. In small amounts, that's fine, but if you get to 10%, 20%, 30% solar PV penetration, you really start to upset the mess, create a mess. So for the folks that have installed solar PV on the roof, they've now paying less for their electricity, which then for the people that don't have solar PV on the roof, you're actually pushing some of the grid costs, the infrastructure costs, onto those people that don't have solar. And if you take a look at who installs solar in the United States, it's typically those that have more income. So you're actually pushing, by trying to be good and install solar PV, you're actually pushing the cost of infrastructure onto the people that can't pay as much for it. And so that's a real social and policy challenge where we're trying to guide utilities and how do they change their electric rates, and how do you pay and what do you pay for. The other thing is if we went to 100% renewables like some nations are trying or states are trying by 2025 or 2040 or whatever the number is, realize that a utility is required to keep the lights on. They're mandated to keep the lights on. They have a requirement to serve is what you would call it, specific technical lingo. As a consequence of keeping the lights on, they need to install natural gas power plants, coal-fired power plants, whatever that might be. Now, a lot of natural gas power plants are going in because natural gas is cheap, and there's very good technical characteristics that provide that in favor of coal. But the resounding challenge is that we're now locking ourselves into using natural gas because those natural gas power plants have a 15 to 20 year financing cycle, and no one's going to stop using those before they get done paying them. Imagine buying a house, having a 30-year mortgage, moving out in 5 years, and then just leaving it empty. That's a stupid idea. Utilities are faced with the same type of thing, the same type of challenge. And so understanding that financial, particularly the cash flow, is critically important for national examples, but even for this one here. And if I went back a little bit to help tie that in, is if in the national electric grid in the United States is about 10 cents per kilowatt hour, and you can pay in another opportunity to provide electricity 200 cents per kilowatt hour, it's going to greatly constrain the type of economic development, human satisfaction, Facebooking, whatever it's going to be that you do, because it's expensive to do that type of work. So what we did is we understood the local needs, but then within the context of the local policy, the village council, and the local social and economic structure, which is very household-centric, and we decided that a microgrid was not a viable solution, because there was no form of taxation, there was no form of community pot or money, and there was no one that could centrally manage it. So we actually went to battery charging stations and solar home systems at the household level because that was the largest socioeconomic unit in the village, was the individual households. And then people went from buying kerosene to using batteries and then charging their home. And so this was a centralized battery charging station, really, really simple design. Solar panel, charge controller, battery, 6 of those in each village. And you would charge a battery during the day. You could use it at night. The charge on the battery would last 2 to 3 weeks, depending on your usage. You had a leasing mechanism where you would lease a battery for $2 a month, and then you would do a 50-cent charge fee. And that is far more economical and sustainable for a household, because if you bought a solar home system, $200 to $400 for installation, that's your entire annual income. And you just don't have disposable assets and no means of loaning money. We haven't been back to Mali in 6 years due to some local struggles, not with us, but actually, the Tuaregs, came down, and there was some civil strife there. So we haven't been permitted to go back. The State Department suggests not to go back. But this has been running, and it's been self-sustainable for 6 years, because we have business managers in each village that know how to repair and operate, and we have a country-level manager that can ship out batteries to everyone or other replacement parts. And so this was a solution that worked out well in that regard. From an engineering design principle, that one I took a look at, and I said, well, now we have a lot of money coming in for grid expansion and for microgrids. The World Bank is going to be putting in $250 million into just 3 countries in Eastern Africa coming up this next year. And so they're going to be rolling out a lot of copper, trying to connect with things. But you have a lot of folks that have solar home systems, battery charging stations, solar lanterns, or local microgrids that they've already invested in. So think back to that natural gas example, is you don't want to have your prior investments be left behind. So how do you integrate those together? What we did is designed a universal charge controller that takes about $1,000 in equipment that integrates all those together, and we made it into a $50 device. So it does the controls, the integration, the communication, the pay-as-you-go monitoring, and it also provides the power conditioning electronics, as you see in that lower side. So it can be used for large-scale solar, small-scale solar, batteries, different types of loads, and then different types of appliances you'd see at the end. And so this is something that IEEE Smart Village wanted us to do. From that work, we were contacted by NRG, and NRG is the largest independent power producer in North America, and so they'd be a competitor to utilities. They also own and operate several plants on behalf of utilities, so they do have some common interests. And they said, hey, this is just after the earthquake in Haiti. Wow, what can we do to help? Not only as their corporate social responsibility, but as a business model, how can we create a national product line and chain that provides for disaster response? And what we designed for them was a containerized microgrid. And so this is a particular model of a 20 kilowatt unit that's in a 20-foot container. And you'd find it on the back of, trains, barges. You can Chinook them in, you can fly them in, you can do anything with that common form factor. There also come in 10-foot segments, which is a quad, and then also 40-foot segments, which is a full container. We did the prototype, the benchmarking, component acquisition, mechanical design, electrical design, fabrication, safety evaluations, standards, and commissioning tests in a 3-month period, going from handshake to turnkey. It's operational, shipping it around the Arizona area for testing. It's since been commercialized by company FastGrid, and you kind of see some of the usage behaviors and characteristics. So this is where I'm going to pause and go over to a quick video to show you some of the students working on this. And this was a really nice project, which was actually a senior design project. And several of the students continue to work for me after. They've done an excellent job. So some of the conceptual designs, this is a bit of the fabrication that we have in our microgrid area, our testbed facility. We ended up going with a simple ground mount because you have 15 to 30 minutes to set it up. Installing racking and cementing things in the ground just took too much time. Noting that we want to keep the donkeys out, so it does come with a fence. So you can't quite see it, but in the back there, it'll actually darken out a little bit. That's installing a firewall to protect the sooner part of that, or the closer part of that, with the solar PV and batteries, from the backside, which is the generator. So understanding standards, regulation, and safety for separating the generator compartment from the battery compartment. And this is just putting in a secondary door to get inside. One of the rare days was actually clouds in Phoenix. A little bit of collaboration. You see on the right there, compression mounts for the solar PV, because when you're shipping things around, you don't have to move. So custom compression racks to hold the solar PV, and then anything that's mounted to the floor has industrial size vibration pads, so it doesn't shift and shimmy, because you don't want to take your phone and throw it against a wall. You also don't want to take $200,000 in equipment and shake it around when you're moving it across countries, etc. The company that we did this work for really wanted that awning. It took too long to get to set up, so we did go with a full ground mount solution. Those are just simple tilt out, but we actually have the newer version has adjustable tilt, because you would adjust the tilt depending on where you are in the world based upon your latitude. And this was a nice project. It's there's a couple of installations around the world. You can get this in Gulf of Mexico, just buy it off of Texas, and it's a 2 to 4 week lead time. So it's customizable. You call up my buddy Eric Hafner, who runs the company. You give him your loads, he gives you back a quote, price information, and then you can get it off free on board FOB on the Gulf of New Mexico 2 to 4 weeks later. And this has been a really nice project. We had it featured in the Arizona Syndicate of NPR just a couple weeks ago, because we had several people questioning us about what can we do for Puerto Rico, and I'll get into that a little bit too. The other thing we started to get asked about is, so you do power, but what about water and what about communications? And if you think about communications, you need power for data origination, translation, receipt, and for water, you need it for water supply, water treatment, etc. And we got a project awarded by USAID to look at water for refugee camps. And we went to do a variety of different assessments. It's for 10 communities in Lebanon, 10 communities in Jordan. And I hadn't done work in refugee camps before. It was actually my first time in the Mideast. But due to the types of practices and design mechanisms I talked about before, we were able to ask really good questions and formulate with focus groups, interviews, etc. Through that process, we actually changed the scope of what we submitted. So instead of focusing on refugee camps, we actually focused on refugee communities, refugee affected communities. There's a couple of really good reasons for that. First of all, when refugees come into your country, everyone wants to help. So you're helping out the refugees, and some countries in the Mideast have been doing that for decades. All of a sudden, you're utilizing a lot of the electricity, a lot of the water, a lot of the resources, and you may not be getting any type of replenishment for that. So the international contractors come in, bring in their own money to help out the refugees, but then they utilize your local infrastructure, but they may not actually be, they may be stressing and straining you even more. One of the things that we found really surprising is that the international contractors, when they come in to do the work, they need some place to stay. No one's going to build a hotel or new housing for the international contractors, and so they're going to take existing houses, buildings, and then convert those to being used by international contractors. What do you need to do to make that happen? You need to kick the current tenants out. That was a big problem in Jordan, where the current tenants, the Jordanians, were being kicked out of their houses, being kicked out of their businesses, and then the local slumlords were then jacking up the rent for the international contractors to come in. That was crap. So we decided to say, we're not only going to help and work with the refugees, we're going to work with the refugee-affected communities and help start some local sustainable businesses where we can create some economic development in these people that are now lost their jobs, lost their homes, lost their buildings because of all of these international contractors that come in with these unintended consequences that they might not even know about. And I knew about it because I was hanging out with people, I was hanging out with welders, I was hanging out with anyone just on the street chatting, and that was something that no one else in our entire convoy even knew about. And so we decided to change the entire focus of the project to create even more local business group growth for local communities. So combine an RO system. That system has been installed in India. It provides water to about 250,000 people across several villages, about 200 villages. With our power system for grid integration to reduce energy costs, increase efficiency, and then if the grid goes down, talking to brownouts again, how does it continue to provide power? And it's one solution for Jordan and Lebanon. Jordan has really high quality power, almost never goes out. Lebanon is not the case. So if you are in remote Lebanon, it might be out for 6 to 12 hours a day. And so you still need water, so how do you get the power to it? At the same time, we are asking questions about more economic development. So how can we not only provide power that meets basic needs, but also drives increased growth? So we're contacted by this company out of Israel, Aora, that wanted us to do some design for their concentrating power, solar power unit. So that's taking the sun's energy, not solar PV, which directly translates it to electricity, but actually focuses it up to a centralized receiver, and then it just gets hot. So the receiver gets hot, it has steam, air, molten salt, metal oxides, whatever it is, and then that is used to drive a typical thermal cycle. This one's interesting because it's an air Brayton cycle, much like a natural gas power plant, so you can offset it with natural gas use in case the sun isn't up, but then you also, in addition to electricity, you have a significant amount of process heat that goes off the back. And if you've ever been in a hospital or an industrial fabrication facility, you need heat, you need steam for a lot of different processes. So it actually led to the introduction of light industry, which provided a lot of jobs, in addition to just the basic need with electricity. If anyone's interested in component diagrams, any mechanical engineers out there? Few? Yay. Good. This is just the operational sequence in the schedule, just to show how it works. Fuel reduction about 20 to 40% in this particular work. So from that work, we also went and designed microgrids, so off-grid power systems. So taking that knowledge of doing off-grid electrical and heat systems and saying, well, whether you're in a disaster response scenario, which is a containerized microgrid, we're looking at large grids or islands in some of our grid modernization work, or you're in an expeditionary force for the military, or a multi-node microgrid for refugee camp, there's a lot of characteristics that we can leverage across all these design types. And so then we looked broadly and asked, what are we going to do for the next 3 years? And so we focused again on one theme of our work on those green parts, which is the microgrid control and integration. Part of that, electrical engineers? Talking electrical engineers? One. So briefly to talk about this, microgrid controls or electrical power system controls are comprised of 3 forms of control. Primary control, which is power electronics, it has to do with millisecond changes. Secondary control, which is scheduling, what do you turn on and what do you set it at? And then tertiary control, which is largely historian, data analysis, and forecasting routines. And so what we did is we architected this so that when you design off-grid architectures or refugee camps, etc., they don't need a higher master level controller, much like the United States electric grid would require to manage and maintain everything in critical operations. And so what it does is it permits the phase expansion of energy architectures. So if you need to change the configuration of a refugee camp or a forward operating base or a disaster response scenario or you're just a community and you've been doing really well for 5 years, so you're going to add 100 homes, you don't need to re-engineer your entire electric grid. You basically just put on another block and everything works together seamlessly. And so that's what this project is. A visual illustration, and everyone loves visual illustrations, is 2 nodes. And so you see there the generators are on a good portion of the day, but this is an illustration with data output why they're using agent-based computation across 2 different nodes, looking at Nash equilibrium, while internally we're using a process which is known as model predictive control to create this at the right side, which is we're sharing power, but we don't have a higher level control mechanism. And you see the amount of generator area that's reduced, creating about a quarter reduction in fuel use, which is critical because fuel is expensive. And if you're in the military and you're using fuel, that's actually one of the largest causes of lost life, is transporting fuel and water around in the military theater. So we applied this work also to the domestic side. And so this is on-grid situations. And the only thing that I'll just briefly say here, you see before our controls and solution are on, the red to green indicates voltage variation, which is not what you want. You could lead to more failures or issues as a result of this voltage variation. And so with our control routines, it actually is far smoother or even. So that's just briefly what I'll say there. Now thinking back as well, as I get to a couple of final examples here, is not only are we working internationally, working with a variety of different partners, we are thinking about how do the electrical skills and how do the thermal skills relate to our projects and problems domestically as well. So we developed a piece of software which is known as a resilient infrastructure simulation environment in an NSF project. And so it actually combines power, water, gas, and transportation, other infrastructures into a single integrated modeling framework. And so I was asking Hans, if you're a mechanical engineer, electrical engineer, et cetera, your typical education and your workforce development will generally be fairly siloed in that regard. You took manufacturing, thermodynamics, et cetera, but how does, if you're in power plants, how does the natural gas turbine and that power plant depend on the security of the outside cyber system, as well as the water, which is used for cooling the power plant, and the transportation to get the gas or the coal, for that matter, actually out to the plant. When you start to take it that broader systems perspective, that usually isn't considered. And that's what generally is classified in the last 5 years as thinking in resilient systems. And so there's natural disasters, Sandy, Irma, that destroy large pieces of infrastructure. But you might be surprised to find out that your power system is vulnerable because of areas of vulnerability in your water system. So we designed the user interface, and then at the end, at the bottom, we simulate different types of cyber or natural gas natural events, and then also stressors, extreme weather events, etc. And I'll give a couple examples of that. So I think my last video for you.
Hello, my name is Derek Hamill.
So here, and I'll actually turn the volume off. So Derek Hamill is narrating a little bit in the background. He's my senior software architect. So we're doing the physical built solutions as well as this computational work. So this is the Phoenix and Tempe area. You see he's turning on and off. This is the power system. That's the water system. And then we've developed the front end, how everything connects together, all the math behind it. And then we use open source tools that model the basic equation sets for steady state power flow and water flow at the end. Power is OpenDSS. It comes from EPRI. The EPA net from EPA is the water network. And then what he's going to show you here is he's going to draw a fault area. So we use this in a design scenario. So anyone in here could design an infrastructure, simulate. We've done climate change events on how does extreme heat or rising heat, extreme heat events, which multiple days at really hot, or just ambient temperature rises, create vulnerabilities and failures in infrastructure. But then also for extreme weather events, which is a more real-time operation. And so like 3 of us in the room would be, or these 6 in the front room would be using this interface, maybe power, water, and transportation. And then I would be that wizard behind the scene throwing different types of faults and failures at you to see how you interacted and maintain and manage in real time. What he showed you here is the pump failed due to a flood. That pump was actually a very large load on the electrical line, and since they didn't communicate and didn't understand their interconnections and interdependencies, the power network on the south half of Phoenix actually shut down. And so it isolated it and protected itself. That load was so large that once it stopped, there was too much power on the lines, and then there was a voltage violation, and then a breaker tripped for safety. Very, very, very common to have those protection mechanisms installed, but there wasn't enough coordination across the operators to really prevent this from happening. And we're working with different utilities, municipalities to go do human subjects research and try out different use cases. One project we're applying this internationally right now is Mexico City, because we're not only looking at the effects on power and water systems, but imagine, who's been to Mexico City? So, thanks, Jesse. It's in a valley. So you have Mexico City in a valley, basically a lake bed. When rain falls, it builds up. You have water pumps that help push the water back outside of Mexico City. But what happens if the weather event is extreme enough that it floods an electrical substation? So now all of a sudden, part of the electrical network goes down. And then if that's a first order effect, the electrical network goes down, and now the water pumps that are supposed to be pumping water outside of the community can no longer pump water. And so the water builds up even faster, second order effect. What do you think happens in a day? What happens in 5 days? Give me some examples. What might happen? Sewage. The third order effect is catastrophic health issues, because we did not properly design the power and water infrastructure to handle extreme weather events. Catastrophic health issues with sewer in the streets that is waste level or higher. That is a major issue. And I was going to say I experienced that firsthand, but I'm kind of glad I didn't, but I told everyone anyway. But I grew up in Iowa, so the floods of '93, same type of situation happened. It's not that uncommon, is the water levels get so high, the water treatment plants dump all their sewage. And then it's in the rivers, and if the rivers are overflowing, it's in the streets. So that's not uncommon. So just think about that if you're ever in a flooding area, stay out of the water. And so now we're looking at those third order effects. Kind of coming to a close here, we've done some microgrid design software with one of our partners out, Zindi. It's out of San Diego, doing an overlay on basic scripting tools to do one-line diagrams and then GIS-based diagrams. Project management tools, we provide a lot of the user testing, the training, and examples. So this is a couple examples from Tanzania. This is an off-grid village. You get the electrical engineering diagram at the left, and on the right-hand side you have more of the project management diagram, which shows you where the lines are to get to the individual houses. Another example, a little bit larger. You see the diagram on the left got it super small. That's because there's a whole lot more houses there. And on the right side, all these yellow lines are electrical cables going between the individual houses. And so we're able to get onto GIS, identify the houses, and then quickly, rapidly design a microgrid and evaluate the cost and technical functionality of that particular system. And that saves, what we found is that versus using current best-in-class tools, this reduces our design time by about 90%, which is critical from a volunteer perspective, but then also if you're a big business, even if it's a big oil and gas, BP, Shell, Total, or if you are microgrid developers like Siemens and other types of groups, you want to be able to get faster products to market. So not only is this beneficial from a volunteer perspective, but it is from a profit perspective for our for-profit partners. The last thing I'll mention to you is that if you're doing design work and engineering work and you have a great impact on the world through that, you might also consider the type of influence and work you could do with other people directly by educating them and training them to do what you do. And so we've developed a several hundred hours, 200 hours of training in microgrid design, installation, maintenance, and safety. And we developed that with some financing and support from the Office of Naval Research to help veterans that have a technical background transition back into the civilian workforce. And that's been extremely beneficial and very rewarding to work with the veteran population there. It's also been great because the classes are hybrid veteran and civilians, and it's helped actually remove some of the stigma from people who did serve in the military that the civilians may perceive them as the other or somehow damaged in some way. So it's been really good from a social perspective in that way as well, particularly for those people that just join the military to pay for education that we're all sitting here for today. The last thing is that, and if we can do the training at Arizona State, One thing we've done is we've built a 7 kilowatt microgrid trainer, so it'd power 2 to 3 homes around here. And that trailer can be towed anywhere, so we towed it from Arizona State out to DC, set it up just off of DuPont Circle, worked with the World Bank for 2 days to do training on microgrids as kind of like a short, vignette or demonstration tool. That was entertaining to be going around the streets in DC, particularly since no one had the capacity to tow a 10-ton trailer, so I was driving the 26-foot U-Haul that did. Fortunately, growing up in Iowa, I knew how to back up duck boats, and so I didn't have a problem running this thing around, but that was entertaining. This is getting expanded, and so now, like in the Navajo Nation, we have a memorandum of understanding and some new work to work with the Navajo Nation that has 3,000 people that will likely be unemployed when the Navajo Generation Station and coal-fired power plant goes offline. And so then they're going to be looking for work. They've been in the energy sector their entire life, really good, hardworking folks. How do we retrain them for distributed energy resources, solar, storage, microgrids, powering off-grid communities in our country? So there's a lot of really good work to do there as well. And with that, I'll pause and actually stop and give an opportunity to ask more questions. But thanks for having me today.